So I wanted to welcome everyone to our next CI Campus webinar. It's my pleasure to introduce today's speaker, Dr. Prasanna Balaprakash. Prasanna currently serves as the Director of AI Programs and Distinguished R&D Scientist at DOE's Oak Ridge National Lab, which directs research, development, and application of AI and ML to solve problems of national importance. His research interests span artificial intelligence, machine learning, optimization, and HPC. He's a recipient of the US DOE's 2018 Early Career Award, and prior to joining Oak Ridge, he was R&D lead and a computer scientist at Argonne. So Prasanna, welcome, and please take it away.
Okay. Thank you, Anirban and Yuva, for the invitation. It's great to be here, and good afternoon, good morning, depending on where you are. So today I'm going to talk about advancing safe and trustworthy AI for science with focus on understanding and mitigating threats to AI data, models, and processes. So this is sort of, I'm going to give a broader perspective within the ORNL's AI initiative, where we are looking into various aspects of safe, secure, and trustworthy, energy-efficient AI. AI is radically changing the way that we do science across DOE complex, and in particular at ORNL. For example, here are some experimental facilities that we have at ORNL. Spallation neutron source, where we use a neutron ray to sort of analyze materials, and these type of analysis produce large amount of data. We are using AI to characterize things, characterize images, characterize the data that are coming out of these experiments, and trying to provide near real-time insights into various aspects of these materials. The manufacturing demonstration facility, we use AI to improve the way that manufacturing can be performed using robotics and using automated workflows and so on and so forth. The Center of Structural Molecular Biology, we are analyzing phenotypes of plants. This produces massive amount, terabytes of data per experiment, and we are sort of connecting those type of facilities to the compute facilities and analyze the data near real time or after the experiments are done, and so on and so forth. Oak Ridge Leadership Computing Facility hosts the fastest supercomputer in the world, and the Frontier supercomputer. And we are using AI to create digital twins of these systems and analyze various aspects of the facility operations, which is very relevant for cyber infrastructure focus of the CI. Cyber Science Research Facility, which is also another key capability that we have, and the facility that is focused on the cybersecurity aspects of various infrastructures that are of critical to the nation. High flux isotope reactor is one where we produce isotopes that are used in space missions and in medical applications. And there, we are using AI to automate various types of characterizations and robotics and robots to do these manufacturing process. So overall, AI is everywhere. And it's quite common that you go across other DOE complex or NSF facilities and so on and so forth. AI is becoming a critical and crucial component of the experimental and analysis workflow. But here are the challenges associated with AI in general. It sort of lacks trust, safety, and security. Why these are important? So to give you some examples from the commercial world, let's say, we are sort of almost celebrating the 10th year of completely autonomous self-driving cars, right? So Elon Musk promised this car 10 years ago. It's not yet there. There is some sort of, semi-autonomy, but there is one thing about doing autonomous cars within a closed control setting, or a car that can drive itself without anyone on the road. There is a completely different thing about, take the car and put it on the road, because that problem is much more harder than people thought. It's not Elon Musk's mistake, but the problem and the kind of techniques that we have to solve this problem are not quite adequate, right? There is also the issue of dual use of AI. So this is a Nature paper that came out in 2022, where they sort of went on this sort of demonstration type thing where say, okay, here is a system, AI system that we designed for drug discovery, and how can someone can use the same sort of AI workflow for doing something bad? And all they did is just take the data. So, the drug discovery data is a toxicity field, right? You want to discover, you want to generate drugs that has less toxic. You don't want a drug that is toxic that can kill patients, but to cure something. So in the process, you have to make sure that it has less toxic. All we need to do is to just change the toxicity values, inverse that value. And now you have a system that can generate very, very toxic chemicals that were never known to us previously, which are synthesizable. That's dangerous, right? So there is one intended use, right, which is drug discovery, noble cause, but someone can take that and really repurpose it for synthesizing potentially toxic chemicals. And this is not a far-fetched idea. So there was a recent paper from Andrew White's group from Rochester, where they were developing a large language model enabled, LLMs enabled synthesis mechanism for synthesizing chemicals. And once they started, putting out the papers related to their software, ChemCrow, people started realizing, this is, you can potentially use that sort of system, right, to explore spaces for explosives, right? So now you have a system, LLM-powered system, that can go and synthesize chemicals for good reasons. And now you can take the same system and it's a completely autonomous system where the LLM-based system was sort of driving the experiments, and this experiment sort of give the feedback about the potential characteristics of the chemical that is synthesizing, and all you need is that feedback, and you can use that to generate good chemicals, right? Drug discovery or whatsoever. But also you can use the same system to come up with dangerous explosives. So they have to pull out many aspects of that package and say, like, we cannot do this, we cannot release this because it's because of the dual use concern, right? So the safety and trustworthiness of these advanced AI systems are increasingly getting important. For the same reason, the government asked the leading AI companies to give voluntary commitment. So this was a fact sheet put out in July 2023, where they came up with these kind of principles, like to ensure products are safe before introducing them to public, building systems that put security first, finally earning public's trust. Right? And here is another memo that was sent by the OSTP so sort of like, what are the priority research directions? And the first one, priority research directions for FY25, right? And the first one is advanced trustworthy AI technology that protects people's rights and safety and harness it to accelerate nation progress. And within those things, you can see, like, develop trustworthy and powerful advanced AI systems. It's not the other way around. You have to look at the order of importance. It's not like develop powerful advanced AI systems and then think about safety and trustworthy later on, right? They want to put trustworthiness as the first class citizen within the whole framework, which is the right thing to do. So the trustworthiness, the safety, the security aspects of AI in the broader context is, these are all getting a lot of importance, both in the commercial world, in the academic, and in the federal government and the labs as well. But it's not an easy problem, right? So all these things. So there is one thing about building a powerful model, that can predict something with high accuracy. But then all the associated problems that comes, it's how to solve those type of problems. It's not an easy problem. So there is a paradox of AI development and challenges. So there are several of them. I want to highlight few of that here. First one, when it comes for AI machine learning, it's easy to demo but hard in production. We have seen that from self-driving cars all the way up to ChatGPT, right? So there is one thing to demo, but it's really hard to put in production. The hard problems are easy and easy problems are hard. So we are right now in a point of civilization where whatever we know up to this point of time from the creation of the planet Earth, we can put that in one single model, right? So as soon as the knowledge is available in the form of text, we can take that, synthesize that, and put it into one single model. That model is super powerful, right? Great. But we don't have a robot that can tie a shoelace, right? It's such an easy problem, but we haven't had a good handle on how to do that in a proper way, right? So that's why when it comes to AI, there are several hard problems that are easy, but several easy problems that are very, very hard for AI. So we need to really understand what are the implications of hard problems, easy problems, how we can solve, and what are all the associated risks associated with, what are all the associated risks. There's ever-growing open research problems, right? So one of the major problem with ChatGPT is alignment, which is model is designed for one purpose, but it can be used either dual purpose, or the model itself can generate toxic content, or it can make up facts that were not available or that are not true. This is what we call alignment problem. And we were not talking about alignment problem last year, this time. Last September, if you go and ask how many research papers or articles that were written on alignment, you will find handful, not many, but that's a major problem going forward. The more complex AI model that we build, we have to worry about alignment. Humans still remain a roadblock, either to build this model. So for example, now we talk about building large-scale foundation models or language models with billions of parameters and so on and so forth. Even in the industry, if you go and ask Google and Meta, how many people can really build these large models and put it into production? You will be amazed. It's not in thousands. It's really in hundreds. That's in the United States, right? So the know-how is sort of not democratized. It's still only few people who can really, in the context of the entire AI community, only a specialized group of people can really pull this out to build large models. And the same thing, only specialized set of people who can solve challenging problems associated with alignment and so on and so forth. It's still in its sort of early stages. There are unique challenges associated with cyber physical systems. There's one thing about developing AI models and keep that within a computer and sort of in a querying like ChatGPT. It's a completely different thing when you take that ChatGPT to drive experiments, to drive a cyber infrastructure, right? To put scheduling, I want to use LLM powered scheduler, or I want to use LLM to drive autonomous experiments. We don't know yet what the associated risks are, in what ways it can misbehave. Are we really comfortable given all these risks, putting using these type of models to drive a multi-billion investment in terms of experimental facilities? The answer is no. So how can we make these models mature and put guardrails in place so that they can be confidently deployed for driving experiments, or to control the cyber infrastructure, or to understand various aspects of data that is coming from experimental characterization and so on and so forth. So there are a lot of problems, a lot of open challenges that still prevents us from reaping the complete potential of AI advancements. There's also a paradox of efficiency. Okay, so there is a Goodhart's law that states that too much efficiency makes everything worse. To give you an example, it's a well-known thing in machine learning, but to give you a general context, there is a thing that we want to optimize, right? For example, in the systems perspective, let's take a supercomputing facility, and we want to optimize the supercomputing facility for what? Probably, to maximize the performance, right? So, okay, so how can we? So maximizing performance is one objective, but how can we then translate that into a machine learning objective, right? Then we say, okay, here is a data about the performance. Let's build a model, and we minimize the mean squared error, right? So that's how we sort of translate the high-level objectives into low-level objective that a machine learning system can be trained on. That is fine until until we cross the well-aligned phase, right? So the proxy measure that we can use to optimize AI systems that actually reflects the original goal, sort of, they are correlated to an extent. But then what happens often is this overfitting case, or the Goddard's law case. The objective that we are interested, let's say, accuracy, mean squared error, R squared, whatever we pull out, that keep on improving, but that does not reflect. That does not reflect in the overall the overall objective, the objective that we want to achieve. So there is a paradox of efficiency, which is very prevalent in AI/ML systems, and we need to be careful about that. So I briefly mentioned about alignment. So here is an example of a boat race, a RL system that was trying to race the boat. This is a game, right? And there the objective is to maximize scores, right? So that's how we translate. Okay, want to win the game, go and maximize the score. So here is where the score, keep on doing this, but so that's how we design, the people who designed the system translated that objective, and everything was going well until the system found out there is a trick to maximizing the score. Just go and crash the boat again and again, and then come back. You will get the turbo mode, and you will keep on increasing the score that you get from this. The game never ends. Right? The system, the agent will keep on doing this again and again. No problem. What we gave as an objective, maximizing the score, that happens. But that was not our overarching goal, right? So overarching goal is to complete the game in a fair way, right? In a way that is fair, and end the game and maximize the score. How can we translate that into an AI objective? Depending on the type of problems, it can be very, very challenging. To give you an example, again, ChatGPT. So ChatGPT, the underlying model, the transformer model, how do we train? It's all about predicting the next token. We take large amount of text, and we construct a series of tokens from the text, and say, okay, given k tokens, we want to predict k plus 1th token. That's it. That's the objective. And if we train that system, we cannot use the system after training, despite the fact that it's multi-billion parameter model whatsoever. We cannot directly use that. We have to do something called fine-tuning and alignment. So the alignment phase is the one that allows the model to sort of make outputs in a way that is not toxic, reduces the misinformation, and so on and so forth, right? So there is this need for aligning these large models to the goals and the objectives that we care about. And often there is this mismatch between what we want and what the AI systems will go and optimize. So the alignment is about ensuring AI systems align with the goals and behaviors. In this case, it could be a human goal, a human values, science goals, and so on and so forth. This is very, very critical as we move forward, because it prevents potential harmful consequences. There are many things that we could think of, and it is very important to align these systems to human values and science goals. There are many different challenges. How to define human values, how to define overarching goals that we care about for a particular context, for a particular application. And more importantly, these things change. Once we test and evaluate the system, the goals change, our objectives change, right? So, we didn't take into account these factors. So how can we bring that as a part of the training, or part of the design process, and so on and so forth. Okay, so there are many different things that we have to take care of. Like, for example, we call that as a guardrails for responsible AI use. So our overarching objectives are efficient decision making, predictive analysis, automated operations, and improved efficiency. But there's the challenges in terms of bias, dual use, misuse. Larger the models, it's very hard to understand what the model is actually doing. If we don't know what the model is doing, how can we deploy that in a confident way in mission critical applications? The complexity of the models, like when you're talking about 100 billion or even trillion parameters, the complexity is just mind-boggling. This is something that we haven't used to work with, to sort of analyze, and so on and so forth. It presents a lot of foundational math and computer science challenges, new challenges. In terms of guardrails, right? So ethics, transparency, explainability, privacy preservation, fairness and security, and many other things, right? So these are the sort of guardrails that should not be an afterthought as it is happening in ChatGPT kind of models, right? So in those type of models, these are like afterthought, right? Okay, we go and train because we can train. We have the access to data, we have access to compute. Let's train the largest model ever possible, and then take that and sort of, go and tinker around to make it work, right? So that's not a scalable approach, right? It can work in this particular case, but if you're thinking about hundreds of different applications, we really have to bring all these guardrails as a part of the design process. How can we design AI systems that look at ethics, that consider the ethical implications, how that takes into account the explainability and transparency, and can protect the data and not leak the data for when it comes for personal information, and so on and so forth. Quality assurance in AI is a very big challenge. So you have seen so many models that were built, and you can go to Hugging Face today and you can find thousands of trained models from industry, from academia, from individual users, and so on and so forth. But if you really ask the question, what is the V&V, what is the validation and verification went into those models, you will not get a satisfying answer. How many of these models are validated and verified properly? Do they come with any sort of guarantees? Do they come with any sort of certificates? It's a big question in front of us. So this is validation is about building the right AI product. This is starts with goal alignment, and it needs proper user testing, and then finally go to the real world performance. And this is an iterative loop. It's not a one-time thing. It's a constant. It's a workflow that is constantly, that will evolve in a continuous fashion, and it's constantly changing. And verification is about building the AI product right. So this needs code model review, model testing, and performance evaluation, and doing this in a loop. Right. So many models that we use, either trained by someone else or even the models that we train ourselves, right? How much of effort that goes into validation and verification? It's a big question mark, right? So, but this is so critical and so important if we are really, really serious about putting AI models in production, whether it is science, national security, or engineering, or energy application, right? So you name any sort of application, we cannot afford to leave this validation verification part and say like, okay, use the model at your own risk. If something happens, it's all you, not me, right? So this can be okay for certain purposes, but it is a critical factor if you are really serious about putting AI into production. Finally, I want to sort of talk about the explainability. So often what happens is, this sort of explainable models work with correlation. Like, okay, so you have the input and you have the output, you find correlations and sort of, try to explain the input to output relationship with correlations. But to make really progress in this field, we had to move beyond correlations and move to causal modeling. It's not about uncovering why something happens, right? So that's what happening in the predictive models. Like, okay, you give this input and there is an output. So that is, we have to uncover that, right? So why something happens, not just like what will happen next. Like, it's not about predicting the next token. We have to predict next token and say why we are predicting this next token in this way. That will allow us to build trust and confidence in the model outputs. So it has different components, but all this starts at the design phase, right? So we had to start from causal variables, and the data collection, model specification and training, and then go to interpretation and validation. And this is a loop. So this is a workflow. This is a workflow that sort of goes in an iterative way with human in the loop. Right? This presents new challenges for us. For us, the typical workflow in science use cases is like start to end, everything automated. It's we do it in one shot and repeat that hundreds of times. But these type of workflows presents new challenges, how to bring human in the loop or how to automate this. And one idea is to use large language models to provide inputs into the causal variables and so on and so forth, right? So really, thinking about various ways these workflows will emerge as we move forward is really a something to think about. So this is an interesting paper on hardware lottery. So it basically says that the idea wins not because of the merit of the idea itself. It's because of the hardware and software. The hardware and software stack, how mature it is. And that is evident in the recent transformer era, because transformers are the architectures that power GPT and other big models. Transformers are like super specialized for GPUs, right? Because of that, we need more powerful GPUs, and more powerful GPUs allow us to build more powerful transformers. And this sort of creates a vicious cycle, and NVIDIA stocks are up, right? So what does it mean for us? Is like, what are all the potential alternatives? Like, is transformer the only alternative that we have? How can we investigate other types of architectures that allow us to make progress, right? So transformers have its own sort of challenges, right? So scaling challenge, it needs lot of data, it needs a lot of compute, whereas many problems doesn't need that sort of that sort of compute and data. Or in many domains, we don't have that many data, right? So data volume is much more sort of restricted. So we really have to think about what are all the alternate ideas in terms of architectures that will allow us to look at problems from different perspective. And also there is a diminishing deep learning returns. And essentially, the more data and more compute, the kind of accuracy that we are getting is not like extraordinary. There are some nice emergent properties coming out of large language models. That is great, but one doesn't need that sort of models for all type of problems, right? So if you care about text summarization, you can get away with million parameter model on your laptop. You don't need to have really large models, and so on and so forth. So there is also this case of like energy efficiency aspect of deep learning. So these are all various types of challenges that we face across AI and applied for science and national security domains. So the AI initiative that I lead in Oak Ridge, the objective of that initiative is sort of focusing on secure, trustworthy, and energy efficient AI at scale for science, engineering, and national security. It has two major components: application component, and that has AI for scientific discovery and complex systems, AI for experimental facilities, and AI for national security. And the foundation components that focus on secure AI, trustworthy AI, and energy efficient AI. So the foundations sort of inform what type of methods can be developed for the applications, and the applications inform what type of foundations that need to be developed. So this goes hand in hand, and these are all not mutually exclusive. For example, AI for experimental facilities can have certain component of cybersecurity, uncertainty quantification, and edge computing, right? Similarly, for national security, we need a lot of cybersecurity, validation and verification, and scalability. Similarly, AI for scientific discovery and complex systems, we need to have alignment, causal reasoning, and a bit of scalability, right? So these are all various ways that we can bring these capabilities together to address specific challenges within those application domains. I'm going to give some examples of the work that we are doing. So the first one is the SECUR AI, again, looking at the goal and behavior alignment. So here we are trying to build models, not just for accuracy, as I mentioned previously, right? So there are healthcare applications that where building a model with a 99% accuracy is not so important. 95% accuracy is perfectly fine, but we have to guarantee privacy and fairness, and we have to have transparency in those models. Similarly, there are models that we build for edge, right, where we have to put this model at the experimental facility, where things can change all the time with respect to noise and the data modality and so on and so forth, where we can sacrifice accuracy to sort of improve the robustness. Similarly, energy efficiency is important for edge applications, where we cannot put a large language model or a large foundation model with multi-billion parameters at the edge, or we cannot put multiple GPUs next to a sensor, right? So we take into account various aspects, various objectives of a particular application, particular domain, and then we train models. One way that we try to do that is to do that in a very automated way. So we use neural architecture search, which is a process in which we define the search space of neural architectures, the deep learning architectures, and then use large-scale computing such as Frontier to explore various types of models. So the whole idea is not to build one model, but to build thousands of different models, and then go and look at the various metrics that we are interested in. And in fact, as a part of the search, we put all these metrics as a part of the training process. So we don't just optimize for accuracy. Let's say for healthcare application, we optimize for fairness and privacy. So there's a multi-objective training that happens with the neural architecture search. And here are some examples. So this is a simple example. It's a 2D, two objective example where we have to reduce the error, which is the accuracy, right? And also the training time. So these are normalized values, lower the better, both of them. And instead of looking at one model, now we are looking at thousands of models. The neural architecture search identifies good models, good regions in the architecture space, and sort of gear the search towards good regions of the search space. And here is the trade-off that you can see. So the accurate models are here, right? So it's lower accuracy, so lower mean squared error. So the accurate models are here. But then if you just sacrifice like 1 or 2% accuracy or 5% accuracy, we can get models that are an order of magnitude less expensive in terms of training time, right? These models are very interesting for several continual learning applications, where we had to train the model again and again and again with new data, where the training cost is a major factor. So now we have hundreds of models that sort of trades off the hundreds of models that trade off the accuracy with the training time. So this is an interesting way to train models and to look at the trade-offs in the objective space. This is another exercise where, again, you can see on the x-axis validation R squared. This is accuracy. And Y and Z axis, you have the time, inference time for the batch inference time, and the number of parameters. So the number of parameters directly correlates with the energy consumption. These boxes, larger the box, larger the network. Okay, lot of parameters. And these colors, different colors, are different loss functions. So loss functions determine the alignment. So how do you use different loss functions? That also determines the type of alignment. So you can see, yes, there are large models with very high accuracy, but also there are much smaller models that has almost like 0.9 R squared and with lower inference time. Inference time is very critical for latency critical applications, right? So where a larger model will have larger inference time, right? Because the data has to go through the entire network, thousands of parameters. Whereas the smaller models can have smaller inference time, less energy consumption, and the accuracy is not far from the largest model that we can build with a very high accuracy. And also it's interesting to note that how just changing the loss function, which is one way to align these systems, can have significant impact, right? So the smaller models, they have all red, right? So mean squared error loss. The best one is mean absolute error loss, which has this error. So this is a lot of trade-offs between the objectives as a function of architecture and hyperparameters. We are also spinning up a new center called the Center for AI Security Research, within which we are looking at methodologies for safeguarding AI data and models from unauthorized access. So for example, if the AML models are very sensitive, we have an enclave, and we sort of use that enclave for both training and testing, and sort of provide ways to secure both models and data. We are also developing workflows that allow us to monitor and monitor the performance of AI/ML models and to audit the AI operations and frameworks. We are looking into understanding model poisoning, right? So how can one poison models by using data or by using adversarial attacks and so on and so forth. So we want to have sort of a risk evaluation framework that allow us to assess how good this model is under various types of poisoning methods. We're also establishing mitigation strategies. This includes securing the data management and robust training practices that gives a sort of a mitigation strategies for AI/ML models. This is one example from this work. This is about privacy preservation, where we have, let's say we have the private data, and the private data, we can, if you train a model on the private data, and if you just leave the model as it is, without taking into account privacy preservation training, then it's possible to reconstruct the data from the model. So instead of that, like what we can do is to do privacy preservation. And one way to do privacy preservation is to change the distribution of the data. So instead of training on the sensitive data, we can find a proxy data that looks like the original data and train on this proxy data. The catch is how far this proxy data is from the original data. If it is too far, the model accuracy will be lower. If it is too close, then we are losing the privacy preservation aspects. It's possible to come up with mathematical guarantees that allow us to characterize what type of privacy preservation that we can put in, right? So there is a knob that we can use use the privacy preservation guarantees to determine, okay, if the user can allow this much of privacy leak or privacy preservation, or if the privacy preservation need to be absolute, then of course we need to sacrifice the accuracy. So there is a trade-off between privacy preservation and accuracy, and we are working on foundational methods to provide this privacy guarantees. So uncertainty quantification is very critical for trustworthiness. So it's about building AI/ML models that not only gives prediction, but also uncertainty associated with the prediction. This is important for various applications, natural sciences, smart grid systems, material sciences, physical sciences. This is not about prediction. So it's about building trust in the prediction. So when the model prediction is good, the model will say, yes, this is my prediction and this is my confidence bound. The model prediction is bad, then it says, okay, my bound is very large. So then that can be used for various purposes. So we are developing foundational techniques to bring uncertainty quantification to various types of science applications. We are also working on this neural architecture ensembles where, I mentioned about using Frontier to explore a wide range of models. It turns out that we can use that sort of capability to do uncertainty quantification as well. So here the idea is to look at thousands of models and then do like a model selection. You can select like 100 models, 100 best models, 100 diverse models, and then use those models to estimate uncertainty. So the goal here is not just use one model to do the prediction, but use 100 models to do the 100 predictions, and from that we can estimate uncertainty. We're also working on validation verification. This is about verifying certain properties of neural networks. So let's say you give a model, trained model, and we want to verify properties such as fairness, privacy, and robustness. How can we do that, right? So there is no sort of, if it is a model, it's really simple. We can do that in a straightforward way. But any sort of realistic models, we have to rely on sampling. So one way is, let's say you have class A and class B, and we want to verify the adversarial robustness of this, like by adding a little bit of noise to an input, does a model move from A to B quickly, right? So this is an intractable problem because larger the number of class and larger the input dimensions, this problem quickly becomes intractable. So we have to rely on sampling-based methods to verify the properties of neural networks and sort of come up with guarantees on like fairness, privacy, and robustness. And this is critical for various types of models, especially if you have 100 models and say, okay, I can verify the properties of fairness and privacy and robustness for these 100 models, then I can go and select the models that have high privacy guarantees or robustness and so on and so forth. To that end, we are scaling up this validation and verification process on Frontier. Here, the idea is you partition the input space and do sort of more targeted sampling and sort of poke the model in various input space so that we can verify the aspects of fairness and robustness and provide probabilistic guarantees, because this is all sampling-based methods. We can sort of come up with probabilistic guarantees that says, okay, this model has this sort of properties, and we can verify them. We can bound those properties and offer guarantees on those properties. They're also using well-safe Citadel framework to do security. So this is about protecting the model and the data. And finally, we are looking into ways to train large foundation models for science. Here, the idea is use large amount of data, scientific data, and train model in an unsupervised way. So previously, we were building more domain-specific models, right? So, ML model for a particular domain A, particular domain B, or even within that domain, particular model for a particular data set. Going forward, what we are after is this way of building large models completely on the unsupervised data, similar to what ChatGPT was trained, and then use that model and customize that model for a number of downstream tasks. Here is one example on CFD. So you can take a CFD computational fluid dynamics data across the board and then train the model, and then use that model as a base, as a prior for applications that use CFD, starting from climate, fusion, and so on and so forth. So there are some internal efforts on training trillion parameter model on Frontier using various types of parallelisms. This is still work in progress. And really the initiative that I lead leverages various types of or various capabilities within the lab. The Kaiser is the one that I mentioned, and Intersect is a sort of integrated research infrastructure capability that connects experimental facilities to computing and so on and so forth. Oak Ridge Leadership Computing Facility and Citadel is the enclave, secure enclave that allow us to do model training and data preservation in a sort of a closed setting. We have launched a workshop series to to bring this and to sort of bring a lot of people into the conversation and train, educate scientists and others on safe, trustworthy, and energy efficient AI. With that, I will end my talk. Thank you for the opportunity and the attention. I'm open for questions.
All right, I think since there are no more questions, let's thank our speaker. Thanks a lot, Prasanna, and it was a great talk. I will have it available on our Compass different channels, like the YouTube channel and other places. And thank you very much for coming. Thank you. Have a good rest of the day.
Thank you. Bye, everyone.